In the last unit, we looked at derivatives and how to take derivatives and the mechanics of the process. In this unit, we're going to be looking at applications of derivatives, and specifically, we're going to start by looking at absolute maximum and absolute minimum, as well as relative or local minimum and maximum. So to get started, before we actually define these values, let's go ahead and look at a graph. If we were to look at a graph, let's say endpoints as such, we could see that when we look at this graph, there are some values that are very distinctive. For instance, this point is the lowest point on the graph, we'll say at A. So at x equal A, we have an absolute maximum. I'm sorry, that's a minimum. It's the smallest that the graph gets, so that's a minimum. And we can see over here, and we'll call this point F. At x equal f, we have an absolute maximum. Now the reason they're called absolute is it never gets any lower and it never gets any higher. So that's why these are called absolute max and absolute min. And we have some other interesting points occurring in here as well that we'll talk about a little bit later. That we have this point that kind of looks like a maximum as well. It's larger than any point nearby. And we have this point over here that looks kind of like a minimum because it's lower than any point nearby. And of course we have these other points as well that kind of follow those same patterns. So if we called these points, let's say B, C, D, and F, E and F, we could say at B and D, definitely something's going on. So at x equal B and at x equal D, I have a max, but it's not the absolute max. So these are called relative or local maximums. It means relative to the points nearby or relative to the points locally, it's the largest value. So that would also lead us to believe then that C and E, so at x equals C and at x equal E, I have a relative or a local minimum. So relative or comparing to the points locally, it is a small value. So starting with the idea of absolute max and absolute min, and then we'll go into the talk or the conversation about relative and local maximums and minimums. Now this is going to get us toward is graphing and modeling functions. We can model functions like cost, the cost functions, because a lot of times a business likes to minimize its costs. We like to minimize packaging surface area so it produces less weight. We like to maximize area, let's say by minimizing length or width. So there's all sorts of different applications that we're going to be looking at eventually. But this is kind of just an overview of how we're going to get started. We already looked at a graph with all sorts of different points, local max, local min, some extrema. Now we're going to break this up into some hollow and filled points so we can further the discussion about extrema. Now this graph, and it's implied to have arrows on either end, which means it goes on forever, it doesn't have an absolute maximum point. However, it does have an absolute min. So this is an absolute min. And it seems to be at the origin. So it looks like we have an absolute minimum at x equals 0. And this minimum value is 0. So absolute minimum of 0 at x equals 0 in this case. Now this particular graph has no absolute max because it continues to grow toward positive infinity. So it has no absolute maximum. Now when our conversation gets further, at this particular point we'll call this an absolute max, but we'll also call it, or sorry, an absolute min, but we'll also call it a relative or a local as we get a little bit more familiar with some of these graphs. Now if we introduce hollow and filled points, we definitely have to have a little bit more conversation about what's going on. Let's just look at half of this parabola. Let's look at the right hand side. So our graph up here was the graph of y equal x squared. Parabola with its vertex at the origin opening up. So now we're still going to look at y equal x squared, but I'm only going to look at on this from the interval from 0, let's say, to 2. So if we looked at this graph from 0 to 2, instead of this arrow being on the end, what would happen is I'd have to stop this at 2. Okay, and we'll say that this is the point 1 and 2. 2 squared would be 4, so this would be the point 4. Now notice I have brackets, and the brackets imply equality. So I have filled points at either end. So I have a couple different things going on here. Here I have an absolute minimum. So I have an absolute minimum of 0 at x equals 0. Now up here I have an absolute maximum of, what was that, 1, 2, 3, 4. So I have an absolute maximum of 4, and I got the 4 because if I plug a 2 in, 2 squared is 4, at x equal 2. So I can see that I have definitely an absolute max and an absolute min occurring here. Well, what if I changed my endpoints around? What if sometimes I had parentheses and sometimes I had brackets? So let's go ahead and look at the same graph, y equal x squared, but let's change the interval on that we're looking at. So let's go 0 to 2 again, but notice 0 is parenthesis, 2 is bracket. So at 0 I have a hollow point, opens up to a filled point. So parenthesis or hollow, bracket is filled. So it has the same general shape, but we can see now down here I have no absolute minimum. Now the reason I have no absolute minimum here is this keeps getting closer and closer and closer to this point but never quite reaches it. So I never actually get to a point that's the smallest. However, up here I do have an absolute maximum. So I have an absolute maximum of 4 at x equal 2. So the absolute maximum value is 4, and that occurs when x is 2. So it matters whether we have parentheses or brackets. Now of course we could have this either endpoint. I could have this a hollow point and a filled point, etc. But you kind of get the idea about how we need to compare those hollow and filled points. And it is important that you take the time to notice that. Now another thing to think about, because I have this hollow point right here, I have a discontinuity at the origin, so at 0. So let's think about what that looks like. So I have a discontinuity at x equals 0. Now the reason we have a discontinuity at x equals 0 because this is not defined and the limit doesn't exist from the right and from the left. But more importantly, the limit from the right of course would be 0. So if we look at this in terms of a one-sided limit, we'd be okay with that second value that we're talking about with point continuity, but the point doesn't exist, and because the point is undefined or doesn't exist, I can't have a continuity here. So this fact that this is a discontinuity, that's going to lead me to the fact that there's no absolute minimum, or in this case I could talk about an absolute maximum if I were to redraw this graph with a hollow point up above. So continuity has to also be coming into play when we're looking at absolute maximums and minimums. This all leads to the extreme value theorem. So the extreme value theorem makes sense once we look at a picture. But written out, the extreme value theorem basically says a function that is continuous, and we just talked about continuity. So a function that is continuous on a closed interval and we're just going to call that interval AB, and because it's a closed interval, make sure we have those brackets in there, it's guaranteed to have an absolute maximum value and an absolute minimum value on that interval. Now we can see that that was true up above. When I had an open point or an open interval on either end, I didn't have that extreme value. So when I have a hollow point, that means I have an open interval, you can see that I don't have that absolute minimum there. So that's called the extreme value theorem, and it makes sense if you look at these graphs up above. I have to have defined points in continuity in order for those absolute extrema to occur. Now when you're trying to locate absolute maximum and minimum values, looking at a curve sketch definitely makes that easy. But sometimes you actually have to look at a function, not just a picture or a graph of the function, but a function itself, and determine those values. Now several of the graphs that we looked at before, all of the absolute maxes and mins were at the endpoints, but it doesn't always have to be that. So let's go ahead and look at this particular graph. So this graph will start at an endpoint with a filled point and looks something like this. Now notice this is definitely the absolute max up in the top left. It's a defined point. But this endpoint is not an absolute max or an absolute min. The absolute min occurs in the middle of the graph, or between points A and B. So this would be my absolute min. So it's not just the endpoints, but it can occur between the endpoints in a particular interval. Let's look at another graph, and this one's a little bit tricky. This one has a little bit of a jump. Notice I have my filled and my hollow points because it makes a difference whether they're filled or hollow. Actually, let's make this hollow at the end. So it kind of looks like this is the lowest value down here, but because it's a hollow point, I never actually achieved that minimum value. So this graph has no absolute max or no absolute min. So no absolute max or absolute min. And this is an important distinction when we're writing these, because talking about absolute extrema is going to be important whether it's a filled or a hollow point, whether it's defined as a filled point or undefined as a hollow point. So knowing those differences kind of clarify exactly what a graph will be looking at. Now we can also talk about corners of a graph, or cusps or sharp points as well. In the next graph that we'll look at, we have quite a bit going on. We'll have some absolute maxes and mins, and maybe some local or relative, and kind of get used to that idea that local and relative have the same meaning. Okay, so for this graph, let's say we start down here at some point A, and we have positive, it's increasing, and then we decide that it starts decreasing, and it kind of hits this corner point almost, and then finishes off with a filled point. So we have several points of interest here. So we have A, we see something kind of is going on here, C, something looks like it's going on here, and E. So let's go ahead and talk about what's going on at each of these points. This is the smallest point over this entire graph. So this point, x equal A, is an absolute minimum. And by absolute minimum, there's no smaller value on this entire interval. Now this is a closed interval, A to E. Whoops, closed. Let me make sure I have those in there. So there's no smaller value on the closed interval AE. So that's what's going on at A. Let's keep looking. If we look at this, this is an important point. We've talked about this one before. This is where the derivative equals 0. So at point B, at x equal B, this is a relative or a local maximum. So when we talk about this point, there's no greater value of the function nearby. Okay, so that's an interesting point. Well, I have the same thing occurring down here. I have a derivative equals 0. And so at x equals C, I don't have a relative max, I have a relative or a local min. There's no smaller value of the function nearby. So important words here, no greater value, no smaller value. So there's smaller values of the entire function, but nearby, relative to this point, or local to this point, there's no smaller values. Okay, let's see what we have going on. Here's C. Let's go up to D. So let's look at x equal D. Now, a couple things going on at D. This is definitely the highest point on the graph relative to all other points. So this is called an absolute max, or an absolute maximum if you want to think about it like that. There's no larger value of the function on the interval AE. Now this interval is a closed interval. So comparing up here, there's no smaller value, and we can say of the function. I can sneak that in here if we need to. I don't think it's totally necessary, but just so it's consistent with the definition below, I'm going to put that in. So no smaller value of the function on the interval, no larger value of the function on the interval. Now, when we look at this point, because I have values to the right and to the left, I can also talk about as being a local maximum. Now remember, local and relative have the same meaning here. So local or relative maximum. Because the points around it, relative to the points around it, it's the largest value as well. But notice I'm not putting in a horizontal tangent line here because I don't have a horizontal tangent line. This is a cusp or a pocket or a square, if we want to call it that. There's an infinite number of tangent lines, so I can't put on that y prime equals 0 here. So that's a lot of what's going on here. Now, with these local maximum and minimum values, basically what we're saying is the points nearby, there's no larger or smaller value that we're looking at. Now, different textbooks adopt different conventions about how they describe some of these types of things, and I would like to point out at A, this kind of seems like it should be a local min, just because this one up here was called a local max. But usually when we look at these closed intervals, or even open intervals for that matter, we kind of look at that and we think, you know what? The minimum value that occurs at the endpoint is not a local min, but it is an absolute min. Because it's at an endpoint, the horizontal tangent line is not equal to 0 here. There's an infinite number of tangent lines, same as up here with the cusp. However, I do have a limit that exists both sides, right and left. Over here I only have a one-sided limit. So those are a couple of things that we look at. Now let's kind of zoom in on part of this graph, and let's see what's going on with slopes. And of course slopes relate back to derivatives. If I just look at a piece of this right here, a couple of different things are going on. And this is going to be point, let's say, C. At this very point, my derivative is equal to 0. That, remember, the derivative is the slope of the tangent line at any defined point along a graph. Now to the left of this point, if we look at all the different tangent lines, we can see all these different tangent lines have positive slope. So the slopes of my tangent lines, my f primes or y primes, I guess if we want to be consistent, my derivatives are positive. They're greater than 0. Now over here on the right hand side, my slopes of my tangent lines, you can see are going to be negative. So we have y prime is negative, which is less than 0. So if I could figure out what this point C was, and then look at the change in my slopes on either side, that's going to help me identify this as a maximum point. Well, I need to figure out where the derivative is equal to 0 basically. And where the derivative is equal to 0, this value of C is called a critical number. So this value of C is called a critical number. Now critical numbers occur two places, where the derivative is equal to 0 and where the derivative is undefined. So I have to keep in mind it's not just one place where a critical number occurs, it's two different ways that that can happen. So let's go ahead and look at critical points. Now another name for critical points is critical numbers. And I'll use these interchangeably, they mean the same thing. So basically with a critical point or a critical number, we can look at the slopes of the tangent lines on either side. And of course, slopes of secant lines would be the same thing, because we take the limit of a secant line to get that slope of our tangent line. So where this occurs, where we have that change, is going to be what we call a critical number or a critical point. Now, if we have any local extrema, they're going to occur at one of these critical numbers. So let's go ahead and write that out. A critical number occurs when the derivative, in this case the first derivative, is equal to 0 or is undefined. Big ideas, very important ideas. So again, critical numbers occur where the first derivative in this case is equal to 0 or is undefined. Now eventually we'll get to taking second derivatives, and critical numbers occur also where the second derivative is equal to 0 or where it's undefined. Now a couple things are happening here. Let's talk about the does not exist or is undefined part. So let's look at a couple of graphs. For our first graph, let's say we have a curve, and we can definitely see we have a discontinuity here, and we'll say that this discontinuity occurs at C. So what we have occurring here is the function does not exist, so that means the derivative cannot exist. So f prime of C does not exist. So there is not going to be, this is still kind of considered a critical value for C, but that doesn't that we have to look at this as a defined point. So again, we could look at this and think, okay, what's going on with this particular point? Is it a local max? Is it a local min? Well, let's go ahead and look at it. I'm going to change this curve just a little bit because I want to force it to be a local maximum point. So if we look at this, even though f of prime of C, the derivative is undefined at C, this is still called a local min. I'm sorry, local max. Having a tough time with my maxes and mins. So this is still considered a local max even though the derivative is undefined because it's hollow at this point. So that's where we're trying to say critical numbers occur when the first derivative is equal to 0 or where it's undefined. So C is still a critical number here. Let's look at another example, and this would be the example of a cusp or a corner. So this would be, again, we want to come to this sharp point here. And we know if we talk about the slope of the tangent line here, the slope of the tangent line is vertical, it's straight up and down. So at this point C, we can see that it's a local max, but we can see that the derivative is undefined here, but f prime of C does not exist, but I still have a local max. So a couple different things going on here, because remember, this is the tangent line right through here, and the slope of that tangent line, or one of these tangent lines, is going to be undefined because it's vertical. So we'd say rise over run, there is no run, so the denominator would be equal to 0. Now a few other graphs can occur. Now just because we have a slope of a tangent line equal to 0, that doesn't guarantee that I have an extrema or a relative or a local extrema. So let's go ahead and look at a graph. In this one, let's go ahead and look at this point C. And at this point C, my tangent line, definitely the derivative is equal to 0 here, but you can see that it's neither a max nor a min. So the derivative at C is equal to 0, but when we look at this, there's no local max and there's no local min. So those are a couple of important things to think about. Now another thing that we can do is we can talk about that vertical tangent line again. So we could have kind of that same curve but turned on its side. Now when we talk about that tangent line at C, f prime at C is undefined. It doesn't exist if we want to think about it like that as well. So we can see that it doesn't exist, but there's no local max or min here either. So what we figured out is, even though the derivative was equal to 0 on the left and the function, the derivative, was undefined on the right, I still didn't have an extrema. So whenever I find these critical numbers, it's not a guarantee of anything. I still have to check it. So let's go ahead and look at some rules for locating critical points. Now once I find these critical points or critical numbers, you can refer to them either way, then I have to test them to see, okay, is this a max, is it a min, or is it one of these strange cases where I have something important occurring with the derivative but nothing is really going on. So let's go ahead and look at a function f of x equals x over x squared plus 1. Well, we know critical numbers occur in two places, where the derivative is equal to 0 and where the derivative is undefined. So we need to figure out what the derivative is. So f prime of x, this is going to be the quotient rule. So I'm looking for the derivative with respect to x of f over g, which should be the bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. So let's write this out. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Now, we can't look at this right now and try and figure out anything. That's why it's so important to be able to simplify these. So if I simplify, I have x squared plus 1 minus 2x squared all over x squared plus 1 quantity squared. So let's keep simplifying. So I have x squared minus 2x squared is negative x squared plus 1 all over x squared plus 1 quantity squared. Now a couple of things I want to note here. X squared plus 1 quantity squared will never equal 0. There's nothing I can plug in here, positive or negative, for x. So remember, critical numbers occur two places, where the derivative is equal to 0 and where it's undefined. So you look at the denominator and figure out, okay, where does the denominator equal to 0? That's going to make my derivative undefined. It will never equal 0 for this one, so I have no critical numbers occurring because of that reason. Now I can say, okay, let's take this and set it equal to 0 then and see what we can figure out there. Well, if we take this derivative, so f prime of x equals 0, it would look like f prime of x equal negative x squared plus 1 over x squared plus 1 quantity squared. If I set this equal to 0, the first thing I would do is I'd clear this fraction by multiplying both sides through by x squared plus 1 quantity squared. And so I have canceling occurring here, and basically end up with negative x squared plus 1 equals 0. I could subtract 1 from both sides, and then I could flip my signs, multiply both sides through by a negative 1, and I get x squared equals 1, which would imply to me that x is equal to plus or minus 1. These are my critical numbers. So again, critical numbers occur in two places. So critical numbers occur, 1, when the derivative is equal to 0, and second, when the derivative is undefined, or when the derivative does not exist. So this basically means, this first part, this basically means when the numerator of a fraction, and it has to be a single fraction, it can't be the addition or subtraction of fractions, this is when the numerator equals 0. And this is just kind of a loose rule of thumb. And again, it has to be a single fraction for this to occur. F prime of x is undefined when I have that single fraction and the denominator equals 0. So these are the two things I need to look for, but it has to be simplified first. And it has to be written as a single fraction. So now that I have these critical numbers, what I'm going to do is I'm going to put these critical numbers in a slope chart. And I'm going to test them to see what's going on. Now the slope chart is just a number line. So I have numbers from negative to positive infinity. If I had endpoints on this interval, I could do that, but this is defined for all real numbers as far as I know. So I have this slope chart, and I put in these critical numbers of negative 1, and x equal 1. So this is just a number line. Now I check and see what's going on either side of it. In the derivative, I want to know what the slopes of the tangent lines are doing. So I check numbers in these intervals to see what's happening. Now I could plug in something, let's say like 2, and it doesn't really matter. I could plug in 3, 4, 5, 6, 7, 8, 9, 10, any of those numbers. So if I come up here and I plug 2 into my derivative, if you'll notice the denominator is always positive. There's nothing I can plug in here. When I square it, I'm going to get something positive back. So I really only care about the numerator because the denominator is always positive. So if I plug a 2 in here, I get 2 squared is 4. Negative 4 plus 1 is negative 3. So I get negative 3 over some positive number, which is equal to a negative value. So I get negative on this interval. Now I'm going to do the same thing between negative 1 and 1. The obvious one to plug in there is 0. So if I plug a 0 in, and again, it doesn't matter about the denominator on this problem because the denominator is always positive. But if I plug a 0 in here, my numerator is positive as well, and my result is positive. So I have a positive over a positive, which is a positive. Now to the left of negative 1, I think we could plug in a negative 2 to see what's going on. Again, the denominator is always positive. There's no number I can plug in here that will make this negative. And so I look to the numerator. So I'm going to have negative 2 squared. Negative 2 times negative 2 is 4. And then I negate that. Negative 4 plus 1 is negative 3. So I'm going to get a negative value here. So what this is telling me is the slopes of my tangent lines are going negative, and then they're going positive, and then they're going negative again. So negative, positive, negative. And I guess this change is occurring over here. So let me scoot that graph over a little bit. So this is called my relative min, and this is called my relative max. Now this only occurs if this point is defined, and x equal negative 1 and x equal 1 are both defined for the function. So I have a relative min at negative 1, and I have a relative max at positive 1. Now if I want to figure out what my y value is, I have to go back to my original function, which is way up here, x over x squared plus 1. So f of negative 1 is equal to a negative 1 over negative 1 squared plus 1, which is negative 1/2. A couple things I want you to note here. I have to have parentheses around the negative 1, or this will be undefined. Make sure you always put parentheses around the base of your exponents. Okay, next one, let's go ahead and plug in a 1. And here I'd have a positive 1 over 1 squared plus 1, which would be 1 over 2, 1/2. So you have to be really careful about how you look at these in terms of our points. Now, this graph is not these sharp points, but on my slope chart, I don't know about the slope and the concavity, I just know about the slope. So for instance, this graph could be opening kind of concave up is what we'll learn to call this, and I still have those negative sloping tangent lines. Or it could open concave down and still have these negative sloping tangent lines. And because I don't know the shape of that, I just kind of draw these as straight lines so far. So these are how I can find my relative max and my relative min. I can also graph these on our calculator to check. So as we look at this graph, we'd go ahead and go into your calculator and do y equal. Remember, we need to make sure you have parentheses around your numerator and denominator just to clarify what's going on here. So I'm going to have x divided by parenthesis, because I need to divide by all of this, x squared plus 1. Now there's several different ways that we could input this with parentheses, but I think it's always a good idea to make sure you clarify what's going on with your graph. Now you might have to adjust your screen a little bit. It almost just looks like a flat line with a bit of a bump in here. So let's go ahead and change our window. I like the negative 10 to 10 on the horizontal axis, but for my y min I want to, let's say, go negative 2 to positive 2. And that's going to really show me what's going on here. Oh, this is really interesting. I can see that this is a min and this is a max, that it peaks out. Now if I wanted to figure out what was going on here with this min, you can go into second calc and then you can say, oh, where's the minimum? So we choose minimum, And this says left bound, and I could move my arrow over, and you see that that little asterisk or star is moving. And I just need to be somewhere to the left of that minimum, and then it says right bound, and I need to be somewhere to the right of that minimum. And then it says to guess, and you can go over and say, well, I think it's right about there. It doesn't have to be anywhere exact, somewhere in here. And you can see that this gives you the minimum value. The minimum value occurs at x equal -1, and that's -0.999 repeating, is -1 and then -1/2. So that matches exactly the work that I found over here working this by hand. Now, something that the calculator shows me that my work by hand didn't show me was the concavity piece, but again, we haven't really discussed that too much yet. So I can see that I have this minimum value here, -1, -1/2. Now I can come back in and find my maximum value. I go to second calc and choose maximum, which is option 4. And it says, okay, be somewhere to the left of the point. And it can be anywhere to the left and anywhere to the right. You just don't want to get too close to that maximum point. And then it says to guess. And you don't even really need to guess if you don't want to. You can just hit enter again after this. And you can see that this occurs at 1 and 1/2. So 1 is my x value, 1/2 is my y value. So our calculator helps to verify these. Now a lot of times when you're going in to find your min and your max, you might not see the min and the max. It might be somewhere off the screen. So you have to make sure that you kind of look around and change your x and y axes a little bit so you can figure out where those occur. So that's an example of how to find your local or relative maxes and mins. As you find critical numbers, you put them in a slope chart, which is basically a number line, and then you test the points and you say, okay, well, what's going on with the slope of the tangent line? Is it positive or negative? And you can do this quick sketch, and then these are my relative maxes and mins as long as these points are defined for -1 and 1. Well, sometimes I want to find not only relative and local maxes and mins, but absolute maxes and mins on an interval. So let's go ahead and put all of these things together in one problem. So let's go ahead and first look at our function, and we also need to have an interval. So we have a couple of things going on here. So find the absolute max and min, and we could also look at any relative maxes and mins as well. So find all absolute and relative max and mins of, let's say, the function, let's do x to the 4th minus 2x cubed. This is a 4th degree polynomial. And let's do this on the closed interval -2 to 2. So we're only looking at a portion of this graph. Well, if I want to figure out what's going on, I think one of the first things I'm going to need to do is find critical numbers. Now this is defined for all real numbers because it's a polynomial expression. So let's go ahead and look at f prime of x. So f prime of x is 4x cubed minus 6. 3 times 2 is 6, x squared. Now critical numbers occur when f prime of x equals 0 or f prime of x is undefined. Well, there's nowhere this is going to be undefined. I don't have a denominator. I don't have any radicals or square roots that I need to worry about. So the only one I need to worry about is where f prime of x equals 0. So f prime of x is equal to 4x cubed minus 6x squared. I want to know where that's equal to 0. Well, I'm going to use my zero factor property. I'm going to pull out a 2x squared, and I'll be left with 2x minus 3 equals 0. So I have 2x squared equals 0, or 2x minus 3 equals 0. Well, x is equal to 0 here, and then over here I'd add the 3 and divide by 2, and I get x is equal to 3/2. So therefore, x equals 0 and 3/2 are the critical numbers. Now they're the critical numbers on the interval -2 to 2. A couple of things to keep in mind. Let's say one of my critical numbers was 5. I wouldn't care because it wouldn't be in this interval. So you always have to compare it against the interval if an interval is given. If no interval is given, that basically implies we use the entire domain of the function. So now that I have these critical numbers, what I do is I look at them and the endpoints and I figure out where my maxes and mins are, and I also check these in a slope chart. So let's go ahead first and look at absolute max and absolute mins. So what I'll do is I'll start with -2. Something important is going on at -2. Then I'm going to check 0. Then I'm going to check 3/2. And then I'm going to check +2. And again, what I'm doing is I'm checking the endpoints and the critical numbers to find out what is the maximum, absolute max, and absolute min value. So if I take a -2 and I plug it in up here, -2 cubed would be -8. -8 times 4 is -32. So I did -32, plug the -2 in over here, and I'd have a 4. 6 times 4 is 24. So it looks like to me I have a -32 minus 24. So I get a -56 there. And again, I'm just plugging it back up here into my original. Now if I plug a 0 in, I get a 0 back out. Now plugging in 3/2 is not going to be as easy, so of course you could grab your calculator for something like that. And so I'm plugging this into my calculator, 1.5 squared, and I get 0 back out for 3/2. That's interesting. And if I plug a 2 in, 4 times 2 cubed minus 6 times 2 squared. And this is equal to 8. So if I look at all of these numbers, I can definitely see a smallest and a largest value. Oh, okay, so now I look at these values, I realize I did not plug these into my original function. I came up here and plugged them into my derivative. So this is my original. I need to make sure I plug these in here. So let me look at this again. If I plug a -56 into my original, or sorry, -2 into my original, I'm going to get all positive numbers back out, and I actually get a 32 here, so I have to be careful. If I plug a 0 in, I get a 0 back out. And if I plug a 3/2 in, I get a -27/16. I thought that was strange we got 0 for both of those, so that's what made me go back and double check. If I plug a 2 in, I get a 0 back out as well. Now, the largest of these values is 32, and so the largest of these values is going to be called my maximum, my absolute maximum value. So I have an absolute max of 32 at x equal -2. This is my lowest value, so I have an absolute min of -27/16. And you usually want to use the fractional form unless it asks for a specific decimal, and this occurs at x equal 3/2. Now remember, we're only interested in this from -2 to 2, so one of my endpoints is the lowest, or the highest, sorry, it's a maximum, and then I have this minimum occurring somewhere in the middle. So we can also graph this on our calculator, so let's go ahead and graph this. And again, be really careful, don't do what I just did. I just glanced back up here and I plugged it into the function I saw, but this is the derivative. I need to plug it back into my original, and you can see that by this notation. So let's go ahead and look at our calculator here. Let's go ahead and graph this, x to the 4th minus 2x cubed. So x to the 4th minus 2x cubed. Now we have to be careful when we graph this. Remember, our interval that we're interested in is only from -2 to 2. So let's change our window just a little bit. Let's go, I guess -5 to 5 would be something a little better. And I guess we could go down to -2. But remember, my maximum value, if you look under here, I had 32. So my y max that I want to look at here, let's maybe go up to 35 or something. Let's go ahead and look at our graph. So I definitely have something coming down here, and then turning and then heading back up. Now remember, I'm only really interested in from -2 to +2. But it's hard to see what's going on here because of the extreme scale. Here it'd be -2, and then this high value up here would probably be right around negative 32. So this kind of gives me an idea that I have a minimum occurring right here at something like 1.5-ish. That must be the 3/2. And I don't have anything occurring here in terms of a max or a min, but I can definitely see that it's crossing at the origin there, and my absolute max would be over here. Now, let's go ahead and look at relative extrema. To find my relative extrema, and extrema is kind of saying, well, either max or min, either way. I look at my number line, and I look at my critical numbers, and I had critical numbers occurred at 0, and another critical number that occurred at 3/2. I check these in my derivative on these intervals. I don't plug 0 and 3/2 into my derivative because I already know what's going to happen there. If I plug 0 and 3/2 into my derivative, it's probably going to be equal to 0 because that's where my function, my derivative, is equal to 0. So I'm going to plug in a value like 2, 1, and let's say -1 here. Now these I am plugging into the derivative. Okay, so I am plugging in up here at 4x cubed minus 6x squared. So if I plug in a 2, let me grab my calculator here, I'm going to plug it into 4x cubed minus 6x squared. So 4, I'm going to plug in 2 cubed minus 6, 2 squared. I get an 8. And that's a positive number, and that's really all I care about, is whether it's positive or negative. If I plug a 1 in here, I get 4 minus 6, which is a negative. If I plug a -1 in here, I have a -4 minus 6, which is another negative. So this one's pretty interesting. Sometimes you'd think that the signs will always alternate, but that's not the case here. So these go negative, negative, and then this goes up to be positive. So again, I need to scoot this over again. That change occurs right here. So I have negative, negative, and then it switches to positive. So I don't have anything happening here. I don't have a relative max or a relative min. However, here I do have a relative min at 3/2, and then at 3/2, remember, if I plug that in, I got a -27/16. So I have a couple things happening here. The largest point on this graph between -2 and 2 is 32, and it occurs at -2. The smallest point is my absolute min, but it's also my relative min at 3/2, -27/16. So this is an absolute min, and then when I check it, I can also find that it's a relative min, but I have to plug it into my slope chart to figure that out. So this is an example where we check for absolute and relative extrema. In order to check for absolute, typically you have to be given a closed interval. That means with the bracketed values. Let's go ahead and pop a picture of this into the lecture so we can kind of remember what this graph looks like. And at some point, pretty soon after we learn about the second derivative in the concavity, we'll be able to create this graph. And usually it's a pretty good sketch of the graph. It's not always going to be identical, but it gives us a nice overview of what the graph will look like. So again, what we have occurring here at this value of 0, it's a critical number, means something's going on, but when we check it, we figure out, you know what, it's not a relative max or a relative min, but what we're going to find out when we learn how to do our second derivative, it's a change in concavity, but for this one nothing happens. And over here at this point, 3/2, -27/16, we can see that this is a relative and an absolute max, or sorry, min. Relative min, and it's also an absolute min. So quite a bit going on there. Let's go ahead and look at another one. I just want you to make sure that you have quite a few different examples to look at when you start working on your homework. Let's look at one that's a little bit different. This one, we're still going to look at absolute and relative extrema. So when we say extrema, that means I'm looking for maxes or mins. And let's go ahead and look at the function g of x equals x to the 2/3 times 2 minus x. And let's look at a specific interval. Let's go ahead and look on the interval from -1 to 2. Now if you wanted to graph this first, you could. That's going to be helpful to you on your MyMathLab homeworks and quizzes. Of course, on a test you won't be able to do that, so don't get too dependent on your calculator. You'll have to be able to work these by hand as well. So the first thing I want to do is find critical numbers. And that's if there are any. There's no guarantee. So critical numbers occur two places where f prime of x equals 0 or f prime of x is undefined or does not exist, however we want to think about that. Okay, so let's go ahead and look at our derivative. This is going to be a product rule. It doesn't have to be a product rule. I could distribute the x to the 2/3 and then just use a good old power rule, but I'm going to stick with the product rule. So I have my first times the derivative of the second plus the second times the derivative of the first, which is the 2/3 x. 2/3 minus 1, or 2/3 minus 3/3 is a -1/3. So I can't really do much with this right now. Remember, I can't use just setting it equal to 0. I need to simplify it a bit first. So I have -x to the 2/3 plus 2/3 2 minus x times x to the -1/3. Now there's a lot of different ways we could simplify this. We could flip this into the denominator. We could find a common denominator. I'm going to simplify this by factoring. Now remember, when we are factoring, I can only pull out the lowest common value. So if I had x squared plus x to the 5th and I was trying to factor this, I could only pull out an x squared and I'd be left with 1 plus x cubed then. So over here my lowest power that's common is x to the -1/3. So if I pull out that x to the -1/3, I'm left with x to the first, because -1/3 plus 1 would be our 2/3, plus 2/3 times 2 minus x. And again, this isn't really ready yet to set equal to 0. This x to the -1/3 is going to flip down into the denominator. In my numerator I have -x plus 2 times 2. 2/3 times 2 is 4/3 minus 2/3 x. And this is all over x to the 1/3. Still not ready to work with this quite yet. I'm going to multiply top and bottom by 3 here to simplify this. And again, this is when your excellent algebra skills come into play. So I have a -3x plus 4/3, -3x over 3 plus 4/3 minus 2/3 x, all over x to the 1/3. Okay, so simplifying, this is common 3. I can flip down into the denominator and be left with a -3x plus 4 minus 2x all over 3x to the 1/3. I can combine my x's here and left with g prime of x is equal to -3x minus 2x is a -5x plus 4 all over 3x to the 1/3. So being able to simplify is crucial. It's very, very important to be able to do this. Now remember, we're trying to find critical numbers. So critical numbers occur two places where the derivative is equal to 0. So for that case, I take -5x plus 4 and set it equal to 0. I'd subtract 4 and divide through by a -5. So I get x is equal to 4/5. And this also occurs where g prime of x is undefined. Well, g prime of x is undefined when 3x to the 1/3, which is the denominator, equals 0. So I could divide through by 3 and then cube both sides, basically saying what value of x makes this 0, and we can see that x equals 0 is where this occurs. So I have critical numbers, x equals 0 and x equals 4/5. So you really have to rely heavily on your algebra skills to be able to simplify this to come up with these values. Okay, so next, I can hardly remember what this problem was about. Okay, I'm trying to find absolute and relative extrema. Let's go ahead and check for absolute extrema. So I'm going to go ahead and just copy my function down again so I don't have to scroll up and down all the time. That was x to the 2/3 times 2 minus x. And the interval I was interested in was from -1 to 2, and that's a closed interval. Okay, so I'm going to check my endpoints. So I'll check -1. I'll check my critical numbers, and only the critical numbers that are in this interval. So I have critical numbers, and remember these have to be on this interval from -1 to 2, and both these numbers are between -1 and 2, but you have to check. And then I have 4/5, and I have 2. Now I'm plugging these back in here into my original. So if I plug in a -1, I get a 3. If I plug in a 0, I get a 0 back. That's our easier one. If I plug in a 4/5, I'm not going to get a nice little fraction or a decimal. I get something like 1.03, so it's approximate. And if I plug in a 2, I get a 0 back out. So the largest of these values is 3. So this is my absolute max of 3 at x equal -1. I have two absolute mins. I have an absolute min of 0 at x equals 0, and I have an absolute min of 0 at x equal 2. So I have one absolute max, and in this particular case I have two absolute mins. And that's not uncommon to come up with those two absolute min values. Now I want to take this a little bit further, and I also want to find my relative max and mins. So my relative extrema. And I'm only going to look at my relative extrema on the interval from -1 to 2. I'm going to copy that function down again too, just so we don't lose it. Well, I already found my critical numbers. My critical numbers were x equals 0 and x equal 4/5. So what I want to do is create a number line, and then I want to see what the slopes of the tangent lines are doing on these different intervals created on the number line. Now technically this is going from, these shouldn't be arrows at the end because I have a closed interval from -1 to 2. So this goes from -1 to 2, and on this interval I have 0 and 4/5. And I want to check and see what's going on with the slopes of the tangent lines. If I want to know slopes of the tangent lines, that's derivative. So f prime of 1, I can't choose f prime of 7 because that's past the 2. I could choose f prime of, let's say, a half is between a 1 and a 4/5. And over here I could choose f prime of -1/2. So let's recall what our derivative even is. So g prime of x is right up here. It's -5x plus 4 all over 3x to the 1/3. Now remember, I don't need an exact value, I just care whether it's positive or negative. Okay, so let's go ahead and plug in a 1. If I plug in a 1, the denominator is positive. If I plug a 1 into the numerator, it's negative. So a negative divided by a positive is a negative. If I plug in a half, what I get here is the denominator is positive. I'm not sure what it is, but I know it's positive. And if I plug a half into the numerator, I get half of a -5 is a -2.5 plus 4 is a positive. A positive divided by a positive is a positive. Let's go ahead and plug in a -1/2. If I have a -1/2, I have a positive numerator and a negative denominator, so I have a negative here. However, x equals 0 and x equal 4/5 as my critical numbers, I can see I have something occurring here. I have a negative sloping tangent line, a positive sloping tangent line, and a negative sloping tangent line. So this is my relative min, this is my relative max. So I have a relative min at 0, and if I plug that back into my original, I get 0. Comes from right here. And I have a relative max at 4/5 and approximately 1.03. So it turns out that 0, 0 is an absolute max and an absolute min, or sorry, an absolute min and a relative min. And this point of 4/5 is just a relative max. It's not an absolute extrema. So we can graph this if we want. It's kind of a strange little graph. Let's go to our y equal. And this is x to the 1/3, or sorry, 2/3. So x to the 2/3. Make sure you have this in parentheses. X to the 2/3 times 2 minus x. And we might have to fiddle with our window here quite a bit. It's going to touch and turn. The -5 to 5 looks good. My y min, let's go -5 to 5 there as well. And again, these are just preferences because I want to get a good look and see what's going on around at the origin. Touch and turn, there it is. Okay, so let's go ahead and have a look at that. Let's see if this matches with what we think. Now remember, we're only interested on this in the interval from -1 to 2. So I can see that I have a min occurring here. Looks like it's a cusp. And then I have a max occurring at about 4/5, 1.03. But this is a relative min because it's only relative to the points around it. Whereas this one, on this particular point, this is definitely going to be a maximum, so we're going to call this a relative max. Let's call it an R max if I can fix that in. But it's not an absolute max. Now let's go ahead and include our endpoints, and our endpoints go from -1. So here's -1 to 2. And so we can see that this absolute min comes in again right here at 0, 0. So this turns out to be an absolute min as well. Whereas this one on this side is going to only be a relative min, or sorry, an absolute min again, because we see that that's at 2, 0, so that's an absolute min. So there's a lot going on here, and we didn't get through a lot of problems, but we sure is a long lecture. There's so many examples that we could do here. We could do trig functions, we can do story problems, but you have the basis of what you need to do to work any of these problems. As usual, if you have questions, please let me know. If you text me and let me know you have a question, we have a new way where we can meet online. It's kind of like the Pearson Connect, but it's a little bit better because we have sound, so we can talk back and forth and do a shared whiteboard. So if you're interested in trying that, go ahead and text me and we can set up a time that works best for both of us. If you're not interested and you just want to send me a screenshot of your problem, that's good as well. Again, if you have questions, please let me know.